Good morning. We continue with our lecture on solidification of binary alloys. We already have 4 lectures on this topic, and this will be the last lecture on binary alloys. And here we will be considering say most of these items which were supposed to be covered in this topic have been covered. We looked at isomorphous system, we looked at free energy composition diagram, we looked up why do we have solubility limit and how these are represented in phase diagram. We looked at reactions involving 3 phases in a binary system. We also looked at some solid state transformations, allotropic transformations. We looked complex binary phase diagram, and we last class I introduced the concept of non-equilibrium cooling. We also in fact solidification process is represented in the form is graphically represented by phase diagrams, and these are the things we have looked at: isomorphous systems, several invariant reactions, allotropic transformations. We also had examples of complex phase diagram involving several of these features appearing in the diagram. We also looked at limitation of phase diagram. See, one of the important limitation is it considered the case of equilibrium, but nevertheless assuming that there is a possibility that local equilibrium exists between the interfaces, that is solid, liquid, or one solid with another solid. It is also possible to explain evolution of microstructures during solidifications and subsequent transformation, and some examples we saw in the last lecture, and we will build upon this and look at it little more critically. Now, here the evolution of structure depends primarily on how the heat is extracted from the system, from the liquid metal when it is poured in the mold. Let us take a simple case, say, which is listed here. Say, suppose this is the portion of the liquid which has been poured in the mold, and the heat is extracted unidirectionally through this directions. Now, there can be primarily this, and when heat is extracted, there will develop a solid liquid interface, and this interface will progress as more and more heat is extracted. This interface will progress this side, and the evolution of structure depends primarily on the nature of this interface. Now, for many some of the calculations we do assume that this interface is planar, but planar interface is always not stable, and it also depends on several factors, not only on the heat extraction, it also depends whether there is supercooling in the liquid or not. And in fact, this expression gives you a heat balance, means how the heat is extracted from this liquid so that it solidifies, and here there will be some amount of latent heat which will come out, and that latent heat also has to be extracted, and this latent heat also the only direction it can flow through is this. Now, there are 2 important things which are important. One, of course, is the cooling rate or the rate of heat extraction through conduction through solid, through the liquid layer, the boundary layer that forms, and it also depends on the rate at which this interface moves. But often these two, the heat extraction and the movement of this interface, they are often related, they are not independently controllable. Now, in case of a simple say pure metal where there is no transformation, we can think about 2 kind of a temperature gradient. This temperature gradient is important because this determines the rate of heat flow or heat extraction through conduction. Now, in one case the heat this a gradient is like this. So, that liquid is at a higher temperature, higher than the freezing temperature particularly, and solidification starts when there is a little amount of supercooling. So, this is you can say this is that freezing temperature. Let us say there will be some amount of supercooling which will be necessary. So, that means here this is the interface. So, here that temperature, that solid interface is slightly lower than the freezing point, and this is how the gradient looks like. Now, here that from the liquid, if the heat has to be extracted, it can only direction it can go is along this. So, here if there is, we talked about, if there is a departure from the planar interface, a bulge develops. Automatically when this bulge develops, heat will come out from these surfaces also. So, which will in fact again so this will not be able to extract it. The only way it can be extracted is through direction. So, therefore, any bulge formation here in this kind of gradient is impossible. Whereas, if we pour in the mold a supercooled liquid, so if that means within the liquid this is the type of gradient you have. So, in that case this kind of bulge formation is stable, the bulging and that is stable and which is reflected here, and this promotes dendritic growth. Now, let us see what happens if there are or there is some solute present in the liquid. And one of the simple diagram that we talked about, a simple, let us look at the solidification behavior of the terminal solid solution in an eutectic system, and this can be applied anywhere. It can also be extended to isomorphous. In fact, this portion behavior is like an isomorphous alloy, and it can be extended to other complex diagram as well. Now, let us take a hypothetical case. We assume that for simplicity to do some calculation, often it is we assume planar interface, this type of planar interface has formed. And in fact, even though overall macroscopic scale it may not be planar, but we can still on microscopic scale in limited region it will still be valid. And here when solidification starts, let us say x 0 is the solute content of the alloy, and here, so this is at any temperature, this liquid S line will give you the composition of liquid, and this will give you the composition of the solid. Let us say for a particular temperature in between here at T 2, this is the composition of the liquid, x L is the composition of the liquid which is in equilibrium with solid with composition x S. And then let us define this ratio is partition coefficient K. This ratio x solid, the composition of the solid to composition of the liquid, we say that this is defined as partition coefficient. And let us take a case where we assume that this is constant. And let us see what happens, and we assume that growth rate is constant, that in rate at which this interface moves is constant. Now, there can be several possibilities, and 3 of these let us look at. One case we look at equilibrium solidification. Here we allow enough time for the composition of the solid to change. The liquid, since the mobility of atom here is much higher, obviously we can we expect that mixing will be quite fast, and for the liquid composition to change we may not need to allow long time, but for the composition of the solid to change we need extensive hold time. That means, let us take a case where the alloy is cooled very slowly and heat is extracted unidirectionally like this. And case 2, let us take up a case where in extreme case there is no diffusion in solid, and here we say that there is unlimited diffusion, that diffusion is very fast. One example is either we cool it slowly or we assume that solid also the movement of atom is very fast, you reach equilibrium through and through as you cool. Now, second case we assume that movement of atom in solid is very slow and there is no diffusion taking place, but still there is perfect mixing in liquid. And a third case where we assume there is no diffusion in solid, but in liquid it is not perfect mixing, this mixing takes place by diffusion. So, let us look at these three cases one after the other. Now, equilibrium solidification, which is shown here, see here when it has just begun, this portion is solid, this is liquid, and intermediate time, this is the situation, this interface has moved to this place and this is towards the end where it has come up to here, the amount of liquid. So, this area you can say this area you can say this is the amount of solute, this area is virtually you can say that is the amount of solute which has moved into solid. So, here we assume that interface is moving slowly and this is the amount of solute from liquid is getting transferred into solid. So, this area will be equal to this. So, intermediate stage here also this area is equal to this, and ultimately when the solidification is about to be completed, the composition of solid, it comes, it starts here, it moves up, here it moves up still further, and ultimately when it is totally solidified, there will be uniform composition through and through. Now, let us take up a case where there is no diffusion in solid, but there is diffusion that there is perfect mixing in liquid. Now, in this particular case, let us say the first solid which solidifies will have this composition which is shown here, and K is this partition coefficient. So, if x 0 we have said that x solid over x liquid is defined as a partition coefficient. Partition coefficient has been defined as this. So, in this case x solid is this, x 0 is the liquid composition, x L equal to x 0, this liquid composition is x 0. So, the first solid which precipitates out will have this composition, and then the liquid, if this much amount is coming out over this range, that liquid will get enriched. So, liquid composition will change along this line. So, at intermediate temperature somewhere here, this is the liquid composition, and the solid composition, see initial first layer which solidifies is this, but next one which is just solidifying now will have a composition which is given by this point and which is x s, and there will be a composition gradient like this, and the liquid composition will shift, will be richer in solute. That means, its concentration will be higher than x naught, it comes here, and this area will be equal to this. So, this is a principle of conservation of the solute element, and in extreme case as it goes down, ultimately you will find that you will reach a temperature here where that liquid will attain the composition of eutectic. This is the eutectic composition, and then the solid will attain this composition, which we say this is x max, and which is represented graphically here. Now, if you write down or try to balance, that means the solute transfer from liquid to solid. Now, if you assume that F s represents fraction of solid. So, this is the total structure, this is F x represents fraction solid, and which is, and now let us say this interface moves slightly towards right. So, that means this changes, there is an additional d F s amount of additional solid is forming. So, in that case, how much amount of solute has to be transferred to solid. So, this is obviously, this will be the difference, the solute concentration difference between liquid and solid, this is x L minus x L. So, this is the amount has to be moved into this. So, therefore, do multiply by this fraction transformed. So, this will be the total amount of solute which will move from liquid to solid, and this will be equal to the change in liquid composition, the change in liquid concentration, the x L. Now, x L, so there will be a d x L. So, this will be the change in liquid concentration. So, what we are doing? So, this area and this area we are trying to balance. So, now, so therefore, this is the conservation. When you apply the conservation criteria, you get this equation, and if you try to solve it, which is shown here, this is a simple differential equation, and which can be solved, and if you integrate it, there will be an integration constant, and this is therefore the expression. After you integrate, what you get is ln 1 minus F s equal to 1 minus k plus constant. Now, to evaluate this constant, you can substitute that initial condition, that when there is just solidification just begins, at that stage x L equal to x 0. So, if you substitute this over here, you get constant, this is 0. So, therefore, your constant is equal to, or which is given here, constant comes out to be this. So, and if you substitute this constant back, and if you go to the screen, you can simplify it and you will get this type of equation. That is, this gives, the first equation gives the concentration of solute in solid as a function of fraction transformed, and this is for the liquid, concentration of solute in the liquid as a function of this is the 1 minus F s equal to the fraction that is liquid, 1 minus F s is actually is fraction liquid. Now, it is interesting, you look at it, this F L, so if you look at this expression little critically, what it shows, that concentration x L is equal to initial concentration times the fraction liquid to the power k minus 1. Now, k is less than sorry, this is k minus 1. So, k is less than 1. What does this mean? So, x L is equal to, say, suppose let us say k is so if this is equal to x 0 minus k is less than 1. So, this will have some power. So, suppose this is let us say 0.5. Now, suppose this fraction liquid, if it becomes very small, in that case what it shows that this increases, this is approaching infinity. So, what does this mean? This means if we go back a couple of slide back here. So, that means as the solidification proceeds, x L can easily reach this point. So, even before that, until the solidification will not be complete until this temperature the composition of the liquid reaches this, and once it reaches this point means you have an eutectic. So, that last solid that will solidify in this case will always be you will always have some eutectic in the last drop of liquid to solidify, even if the amount of solute in the alloy is very low. Now, let us move on to a case where there is no diffusion in solid, but there is mixing by diffusion in liquid. Now, in this case the few cases which have been represented here, let us consider the similar system exactly here. Say suppose at this temperature say T2 somewhere here. As we have seen, the first solid that will solidify, we will have this composition k times the partition coefficient times x naught. This is the initial solid, and final solid at that solid liquid interface will have a composition which will be given by x s. So, this temperature it is given by at this point, any point on this solid S line. So, which is shown over here, and now what happens is, where does this since some solute, there obviously will be some build-ups, because we are assuming that when this transfer is taking place, the composition of the liquid far away is x naught, but when the solid is rejecting the solute, it is going into the solid liquid interface. So, the composition will build up over here, and let us say this has gone up somewhere here, and after a certain distance it becomes equal to the x naught. So, because of this concentration gradient, there will be some diffusional flow of solute from this higher concentration to lower concentration. So, in this case also, therefore, we can build up similar using conservation principle, we can build up a equation that will describe how the solute gets redistributed in the liquid. Now, here if you progress, if you cool it further, it will come down somewhere here. Let us see at this particular temperature, and it has been found, and experimentally also, that after certain time what happens when you reach this temperature, you get a situation like this, that solid composition becomes equal to the composition of the original the alloy, that x naught, and we assume that after that the solid composition does not change and the solidification is completed at temperature T3. In that case, we have some kind of a steady state situation. It comes here and it comes you get a steady state situation, and this composition of solid thereafter does not change, but at the interface there is that build up is still there, and this is the build up. This is the concentration profile in the liquid, and it proceeds further, and towards the end there will be some amount of eutectic, towards the end there again will be some transient, towards the end of the solidification again there will be some transient, we assume. So, that means there will be a stage somewhere here where there will be a balance and there will be a steady state, and after it reaches the end, then again that liquid will try and get enriched. So, this is something like this. That means, towards the end there will be a large difference in composition in the liquid, where liquid will have a build up, and here it may reach that eutectic composition. And now, let us see that what this equation, if you balance the solute movement, what type of equation do you get. Now, if we say that x L is the liquid concentration and x naught is the solid concentration when the solidification starts, and we assume that this interface moves with the velocity v. So, in unit time what we have is, so amount of solute transfer will be v times x L minus x naught, and here so therefore, there will be some amount of that solute has to move through the liquid, and let us say that liquid there is a concentration gradient set up, and this distance we represent by this direction we represent by y, and then this is the diffusivity d in liquid, and then this is the equation which describes the solute balance between solid and liquid at this interface. And once you solve this, this also is a very simple equation which can be solved, and this solution which is shown over here, and when you integrate there will be an integration constant which you can evaluate by this initial condition. And once you evaluate this by that initial condition and you substitute the constant back, what you get is the concentration profile, and you see that this profile has an exponential character. So, that means and if you try and plot, that means the concentration in the liquid will be equal to x naught one minus then an exponential term minus, this is the distance over d minus v. Now, here look at this dimension of this is also that of a distance, and this is called a characteristic distance. Characteristic distance for the concentration profile. So, that means from that interface, say suppose this is the interface, and here your concentration at the interface is x L, and as you go in this direction y, your concentration is changing like this, and at a large distance it becomes equal to x. So, this is x L, this is x naught. Now, if you go back to the previous expression, what we said that so this is x L minus x naught is this. This if we divide by d by v, this is equal to d x L dy. this is negative. Okay. This is the expression. That means solute balance gives this. So, that means if you draw a line here, the tangent, then this distance is equal to d by v, and and it is quite important to look at what is the effect of this magnitude of this characteristic distance of the concentration profile, and this is shown in this diagram. This concentration profile has been plotted here, and this is the tangent at that interface, and this side is solid, this portion is the liquid, and here is a build up of concentration in liquid, that it is much higher than the concentration of liquid far away. So, there will be a diffusional mass transfer along this, and we are considering that steady state diffusion only. And now, and let us look at side by side the temperature gradient, or how does this temperature plot would look like. Now, here the temperature, if you plot here the temperature just down below, this side is solid and the solid is cooler. So, this is the temperature of the solid. So, this is the temperature of the solid liquid interface under that steady state growth or movement of this interface, steady state movement of this interface. So, this is, we have seen that if you refer back to the phase diagram where these temperatures are have been marked. So, this is the T3 temperature, and now here what happens is and the temperature far away in the liquid is this, and far away in the liquid its composition is x naught. So, T1 you can say is the liquidus temperature far away, and now you look at this concentration profile, look at this concentration profile. With this profile, if you go and with this profile you refer back to the phase diagram, that liquidus point. Say suppose here this is the concentration in the liquid, that is x naught. So, therefore, here its melting point or liquidus point will be here, and here is the liquidus point, and in between that liquidus temperature profile will be like this. So, this we say that this is the temperature, that equilibrium temperature of the liquid which is existing in front of the just near this solid liquid interface. So, far away its temperature is same as T1, but in between the transient zone it has this is the temperature of the liquidus. Now, let us look at what is the temperature gradient that we are maintaining, and this is the cooling condition, that mold condition is such that we are able to maintain, this is the gradient, this is the temperature of the liquid. So, we maintain a gradient in the liquid, temperature gradient. So, as you move inner the mold, the temperature is higher, and this is the solid temperature. Now, in that case what we have a region here where there is supercooling. So, even though the gradient is positive, so refer back to the pure metal situation. Unlike that, here even though you have a positive temperature gradient, there is supercooling. So, here you can say that this is where your planar front will be unstable. But look at this case, if you are able to maintain this gradient, that means this distance, this is the distance So, at this distance if you are able to maintain that tangent, you draw this tangent to this. So, if this gradient it matches this, in that case what we can say, if this gradient, try and find out what is this gradient. This is the composition temperature profile, and let us try and find out this temperature gradient. And if this temperature gradient is greater than the critical value, or you can say that this temperature is, you can say this is the critical gradient, temperature gradient. So, if this temperature gradient, that means first differential of this with y. So, if this is greater than that critical gradient, in that case we say that one can infer there is no constitutional supercooling, therefore, planar interface will be stable, and otherwise there will be deviation from planar interface. And so, this is so therefore, in this particular case you will try and you will tend to get you go back, and this condition which is listed here, look at this. If that means this is the critical gradient, and if the actual gradient which you are maintaining, that this T L gives the actual gradient, the differential of this line with respect tangent of this, that d T L over d y, if this is greater than this gradient, that is T 1 minus T 3 over this distance, that this is the distance, characteristic distance. In that case, you will have constitutional supercooling. So, if this is greater than this, then the planar interface will be stable. If that means, if this slope, the gradient is on this side, you will have planar interface. If the gradient on this side, you will have dendritic growth. So, in this side you have planar, and this side you have dendritic growth. So, looking at this diagram, you can say, or this type of relationship, you can see that it will be difficult to get planar interface in alloys where this temperature is very high, and also if the cooling rate is very high, the V, that rate at which that interface moves, if this is high, if the cooling rate is very high, it will be extremely difficult to get planar interface, and having, and also if the alloy has wider freezing range, then also it will be very difficult to get a planar interface. And now, let us look at say little departure, let us case. But in reality, if you look at alloy system, the alloy, they rarely solidify with planar interface, and the temperature gradient and growth rate, they cannot be independently controlled, often they depend on heat transfer rate. Now, let us take up a case and see when cellular structure develops. Now, we will come to know what is cellular structure. Now, suppose if the temperature gradient is initially favors planar interface, and in gradually, so initially you are able to maintain say a gradient on very high gradient, and later on it moves this side, and which is in reality it is possible in alloys, it is possible in reality. The reason is, if you look at you have a mold and you pour a metal, so initially that liquid here you have a very high gradient. The mold is temperature will be much lower, and when you pour the metal, initially here the gradient is very high. So, on the surface the initial gradient is very high, and then let us say in that case the interface is planar, and after that the gradient, when the solidification proceeds, this thickness grows. So, heat has to move through this. So, the gradient decreases. So, later on say it comes to this side. So, that means there is a departure from the planar interface, is gradually it is reduced. In that case what happens, this kind of bulge will now be stable, and in this case there is a constitutional supercooling. So, even if there is some amount of heat can be accommodated this side. So, what happens when this heat is accommodated on this side, it will also go there. So, what happens later stage, it develops this side, there may be some amount of melting again, and this type of, this is how it starts growing. And you grow further time, then you will find this type of structure develops, and this is called cellular growth. And here you have the liquid, the solute is also getting rejected here, So, now clearly, and whenever and it is quite likely. So, here if you have an eutectic type of alloy, what happens when it starts cooling down, towards the end there will be some eutectic solidification here. So, here you have liquid, here it is very rich in solute, in this end very rich in solute, here it is leaner in solute, this portion it is leaner, and here when it reaches that eutectic composition, this composition, it will get converted into an eutectic structure. So, what you will have is here, once the solidification is complete, you may get this type of a structure here, and here you have eutectic. So, that means in these channels here you will have eutectic structure. So, this is what type of structure which will develop in a mold. Initially, because of high gradient, you may have a planar interface. This will be the chilled zone. Then you have this kind of a cellular type of structure. So, this in reality you do get it. So, that means we have made a lot of assumptions, and based on that we have tried to understand how the solutes get distributed in the liquid during the process of solidification, and it results in structure which are which can be explained, and the criteria of the type of structure that you get is, if you have a planar interface, in that case the gradient should be greater than the critical. In case of a cellular structure, the gradient is slightly lower than the critical, then you get a cellular structure, and when it is much less than, significantly less than the critical, in that case you will have dendritic type of structure, that this grain. So, these will be dendritic type of structure will develop, and here also this liquid which is present here, they will convert into eutectic. So, you do get this type of structure in alloys, and here and this redistribution of the solute, in fact, this is there is a general term, we say that this is called segregation. So, as a result of this non-equilibrium cooling, solute is not uniformly distributed, and this is called that solute is segregated, and that solute segregation is called, this is one type of segregation, it is a micro segregation. And if this dendrite, if you want to make them uniform composition, you have to heat it, and if this dendritic structure is very coarse, in that case it will take very long time, you may have to heat it for very long time to make this composition uniform. But if this dendrite, they are smaller, they are thinner, if these cells are thinner, or if these dendritic arms they are thin, in that case that time which is required for homogenization is small. And now, let me give a couple of example of segregations. Say one, you have all of you have must have seen ice cubes, and these ice cubes actually it's which you grow in home, say in a chill tray, if you you try to grow the ice in the freezer, and you look at the ice, take out a cube, look at it, you will find that the edges they are transparent, whereas at the center it is foggy. This is actually a clear case of segregation. And why does this take place? Now, water actually has dissolved gas, that means air is dissolved in water, and air and water it forms some kind of an eutectic phase diagram. So, so let us assume that water, this is pure, eutectic temperature is this. This is the eutectic composition. So, the first that ice that will form, say this is, let us say this is the container, and heat is extracted from all sides, let us say. In that case, the first layer that ice will form a planar, and this will go on rejecting the air to the water. So, this becomes richer in air, air concentration increases here, and ultimately when it reaches this this particular temperature, that is eutectic temperature, then both solidify together. That means, ice will form, but in the meantime a crust will form on the top of the ice, because heat will be extracted from the top as well, and the ice is lighter. So, therefore, ice puts a cover, and this air which is trapped is also not able to come out. So, once this ice crystals form here, so the air bubbles will also get entrapped between, you can say, the dendrites of ice, these are crystals of ice, and in the channels, the crystals of channels, there will be air bubble, and this is what you see. So, in reality here you can say this is the defect free, segregation free region, and air has segregated in the central portion, and this is what you get when you solidify alloys as well. When you solidify steel also in a large mold, here also the steel will have dissolved gases, these gases will go to the center, and the meantime if the top has solidified, the gas cannot come out. So, in the central portion you will get gas porosity as you, and in fact, these porosities will be present in the interdendritic, that crystal, these channels. And this is a type of segregation. The solute elements also do get segregated, and amount of segregation will be more to the center of the mold. If you go from the mold wall, here it will be purer material, and segregations. solute concentration in the center portion will be more. And also in the liquid there are other movements are also possible. The movement due to convection, there will be temperature difference in the liquid, the lighter liquid which has lower density. When it cools, the liquid cools, that the density increases. So, that therefore, the cooler liquid will move down, and this kind of convection current will be set up. Similarly, the solids which form, the crystals which form, and towards the end, say if this is the mold, you have this type of cellular structure. This is forming from the wall side. Crust has formed, and these are the columnar grains which are forming, and towards the end you know, the supercooling here becomes so large, you will get crystals here also. If these crystals which are heavier than the liquid, they settle down, and so towards the bottom of that ingot also sometime you get negative segregation. The first solid which that precipitates out, they are purer. So, you get negative segregation here and positive segregation in these parts, and this segregation you will always get in alloys, and by controlling, and one way you can control is control the processing, that nature of segregation, the extent of segregation, and if you have to get if some of the segregation which are macroscopic, they will be very difficult to remove by any subsequent heat treatment. You have to. So, one way will be that type of segregation which you get, which are very large, which you can see by naked eye, which will be very difficult to remove. But if you have microscopic segregation, say small crystals have formed, and there is a difference in compositions, or small these dendrites have formed, the dendrite arm they are finer. In that case, the width is less. So, here if you heat it, that composition uniformity it may be possible to achieve, but if you have macroscopic segregation, then you have to do subsequent downstream processing, maybe large deformation to make it uniform. So, with this we finish our lectures on solidification of binary alloys, and later on we will build upon it and look up more complex systems. And what we have looked today is we use the concept of local equilibrium to reason out, to find out the type of structure that develops in alloys during solidification, and we also looked at the instability criteria for planar interface and why you get, and we also found out why we get eutectic in terminal solid solution, and we also looked at the cellular difference between cellular and dendritic structure and when do they form. We also talked about segregation, both micro and macro segregations, and later on in subsequent lecture maybe we will be using some of these concepts and apply them. Thank you.